In the last class we had talked about how the plug nozzle would have a better performance, off design performance. Let us look at it in this graph. If we have PC by PE on the x axis and CF on the y axis, this is a log scale. So if you have a nozzle designed for some high altitude condition somewhere here, a conventional nozzle or a conical nozzle will go like this. Whereas a plug nozzle will have a superior performance throughout. This is so the conical nozzle has a much inferior altitude at conditions other than the design conditions. Its performance is not as good as a plug nozzle or an aerospace nozzle. Okay. So next we move on to the other topic, that is thrust vectoring. Right. Thrust vectoring is something that is used by all missiles as well as launch vehicles. If you look at the tactical missiles, that is, these are small rockets, and if you look at what is the level of thrust that they produce, the accelerations that they have initially is of the order of 10 g. So they very quickly go to a very high velocity. Okay. So which is why you do not need any control in the boost phase. They usually have something known as a boost phase, wherein the thrust is very large and it goes to very high accelerations due to gravity. The acceleration achieved are very high, and after which they will have a sustained phase which will essentially keep it at that particular Mach number. Okay. So for such rockets or tactical missiles, aerodynamics is a very good aerodynamics offers very good way to control the motion of this, as in if you wanted to veer around to a target and other things, you can have fins and you can make it go towards the target very easily. But if you look at launch vehicles and strategic missiles, that is long range missiles, when they take off, their accelerations are very small, typically of the order of 1.6 g to 2 g, right. They are not very large. So as they are going up, they are going up very slowly, and crosswinds can take them in a direction that is not intended if you have strong crosswinds. Launch vehicle, you can put off the launch by a few hours. You can say till the weather gets into some kind of reasonable conditions, you are not going to launch it, and you will wait for that time to launch it. But missiles, you cannot afford to do that, because you need to be ready every time. Okay. even in launch vehicles you would still want some kind of control in this period of launch wherein the velocities are very small. Up to the time that it reaches a Mach number of around 0.5, aerodynamic control will not be very effective, right. So it is unlike aircrafts, where unlike aircrafts will have a very large surface area, right. The wing span is very large, so it can produce substantial lift. Here you do not want it to have so much drag associated with any control surface, you want it to be minimal, so you will have very small fins. So for under these conditions you would need something known as thrust vectoring, that is, can you change the direction of the thrust itself so as to take the vehicle in the direction that you want it to go in. In addition, if you have looked at launch vehicles, let us say PSLV or something like that, you will find that it has a main core and on the side it has small strap-ons, right. PSLV has 6 strap-on motors, now the nozzle of all these boosters are in such a way that they are canted away, that is, the thrust that it produces is at some angle to the vertical axis, right. So if this is the axis, then the thrust produced is not parallel to it, but at some angle, right. So if all of the thrust vectors meet at some common point on the axis, then it is perfectly balanced, otherwise there is some imbalance and you need to have a counter force to overcome this, right. You need to have a control force capable of overcoming this, otherwise the vehicle could veer in a direction that is not intended. So for all these things you need this thrust vectoring, okay. Now thrust vectoring can do all this, that is, it can allow the vehicle to roll, yaw and pitch. In this class we will concentrate on what are the ways in which we can vector this thrust, what are the means that are available and what is it that is practiced and what can also be done, okay. Now typically thrust vectoring, there are 3 modes that are usually followed. One is gimballing of thrust chamber, or nozzle, or introducing mechanical control surfaces or secondary fluid injection in the exit cone. We will look at each of them in a little more detail in this class. Now firstly, gimballing the thrust chamber or the nozzle. If you look at a liquid engine, liquid engines typically the propellants are not stored in the engine or in the chamber where it produces thrust, that is the fuel and oxidizer mix and burn. So it is stored in a separate chamber, so the engine itself will be very small. So you can look at moving the engine in two different planes to get the control force that you require. Okay, that is possible in a liquid engine. That is, if the engine were hinged on this, you could move it around by an angle alpha in either direction, and if you have something known as a universal joint, universal joint is nothing but if you have two hinges, right. If you have two hinges like this, using one of them you can move it in one plane, using the other one you can move it in the other plane, right. So using both of them you can move it in two different planes. That is what is a universal joint. If you have the entire engine mounted on a universal joint, then you can move it in this plane by alpha and also in the plane perpendicular to the board by an angle alpha. Okay. So that is what a gimbal or a hinge will do. As you can see, if the engine is moved, overall engine is itself moved by an angle, then the thrust produced will be the cos of this angle, right. So it will be lesser than the actual thrust. So you are going to lose some amount of thrust by vectoring the thrust itself. So you can, using this, move the entire vector the thrust by plus minus 12 degrees, and there will be a small thrust loss, and this is typically used in only liquid engines. That is because, as I said earlier, if you look at solid engines, the entire propellant is also inside the motor. So it would be very difficult to move the entire motor because the weight of the propellant is also there, whereas in a liquid engine the propellant is stored elsewhere, and only thing is you need to have flexible hosing, otherwise it will not allow this kind of movement. Okay. So you need also large actuators to move this. Okay. and the critical thing is, if you look at this, the entire thrust of the engine is transferred through this hinge or the gimbal. So this needs to be very carefully designed, because this is a very critical parameter, I mean very critical element, because the entire thrust is transferred through this element to the rest of the vehicle. Okay, so this needs to be carefully designed. Instead of gimballing the entire engine, the other option is, can we just move the nozzle itself, and that is called as flexible nozzle. So if you have an actuator and move this nozzle alone, right, then you can get the same desired effect of vectoring the thrust. Only thing is, this joint needs to be flexible here and allow for movement. Okay, this can also give plus minus 12 degrees, and again there will be a small thrust loss, because you are anyway vectoring the thrust. So the cos of the thrust is the only one that is available in the axis, along the axis. This has also been used in both solids and liquid rockets. Here you can use it in solid rockets primarily because you do not have to move the entire motor, you are only moving the nozzle, but still the actuation force required here is also quite significant. You need the last of this variety is, again, if you have something like a ball and a socket joint instead of this one, you can move the nozzle Okay. If you have it mounted on a bearing, then you can move it and therefore get the required thrust vectoring. Now, in both these methods, the nozzle in some sense is submerged inside the motor, and this leads to something known as submergence loss. Primarily, if you look at the gases coming out, they need to, you would also have propellant stored in this direction. If it is coming in this direction, it is a lot easier. Otherwise, the gases coming from burning of the propellant in this region will have to turn through a large angle, and that will lead to some losses, because the flow will now have to turn through a large angle to get to the nozzle, and that is given by something like, it varies between 0.4 to 1.2% loss in ISP. And if you remember the discussions that we had in the morning, that is, if this propellant were aluminized propellant, right, then we discussed that the particles don't, or condensed particles do not expand and they cause loss, right. This gets coupled with that, and depending on the percentage of aluminum present in the propellant and the amount that the nozzle is submerged, the loss could be higher. I mean, this, it is within this range. It could be higher if it is more submerged, lesser if it is less submerged. Okay. The next set of control that we can get is from mechanical control surfaces. Here, if you are using mechanical control surfaces, what you will have is something jetting into the exit flow, and therefore you are going to obstruct the flow and cause the required thrust vector. Okay. Jetavators are something like this. If you have a rocket motor, this, at its normal position, it is something like this, and if you want to have a side force, you could change its position to something like this. So, this does not protrude into the flow in its normal position, but when you change its position, on one side you get over expansion and on the other side you get a little bit of under expansion. This causes a side force. Okay. So, you are going to get a small amount of thrust vectoring. If you are using this, you will get something like plus minus 7 degrees of thrust vectoring, and compared to the previous ones this is a lot better in that sense that firstly it does not require a very large actuation power, right, because you are only looking to actuate a small surface and therefore the power required is smaller here. These are used in solid rockets. Yeah.
Which part is rotating in this?
This small portion, this dotted line, it is in line with the nozzle when it is not doing anything, right. You can then rotate it, and on one side it will be flush with the nozzle. So it will act as on one side it will over expand, and on the other side it will under expand, and therefore give you the required side force. Okay. Then there are some things known as jet tabs. Now if we were looking at it from the bottom, it would look like this. Now you could move this into the flow as per requirement, okay, and depending on the amount this obstructs the flow, you will get the thrust force proportional to that, okay. So as such this does, both these do not obstruct the flow in their normal position. So, they do not add to any loss in their normal operation, but when they are used they will lead to a small loss. With this you can get plus minus 14 degrees of change in the thrust, and whenever this is in use it leads to something like 1% loss in thrust per degree of deflection. Okay. And the actuation power here is also very small because you are only trying to actuate a small tab. So, the actuation power required is smaller here. The last in the mechanical control surfaces is something known as a jet vane. These jet vanes are in the exhaust gas flow. Okay. So, because they are present in the exhaust gas flow itself, even without actuation they are going to lead to some kind of thrust loss. Okay. So, they are going to have, you are going to have some thrust loss you can get thrust vectoring of the order of plus minus 9 degrees, and the thrust loss will be more when it is actuated. Okay. It is there even without actuation in this case, and it will be more when it is actuated. So, this needs pretty good heat resistant material, because it is always in the exhaust flow, right. What is usually done in the case of jet vanes is you might need this for a small period of time during takeoff or during some critical operation, after which you can throw them away. Okay. So, these are used in some examples wherein you are launching something from a ship or launching a missile from a ship or something like that, then it has to turn by a large angle. So, you can use this and then throw this away, and for the rest of the flight this is not useful. Okay. So, it is used for a very small period of time, Now the last thing that is used actually in rockets is the liquid injection. Remember in our earlier class we said if you have an oblique shock, the flow separates and it will introduce a side force, right. In this method of controlling or thrust vectoring, we actually make use of that and we inject a liquid at some known point in the divergent portion, that is, let us say we inject the liquid at this portion. Because of the liquid coming out here, an oblique shock develops upstream of this liquid injection point, and because of this you will get a side force, right, because in this portion it actually acts as a nozzle being cut off and after some length, and therefore it gets you the required side force. Okay. SITVC is used in PSLV's stage 1 motor for thrust vector control. In this case, because of the liquid injection, there is a small amount of thrust augmentation that is happening. The liquid that is used is strontium perchlorate. Now the reason for using such a liquid is if you look at the momentum of the jet that is coming through, if you are injecting this jet needs to have a higher momentum than the jet. Okay. So rho j Vj square must be comparable to rho g Vg square. Now if you notice here, the density of the gas is very small, and but the velocities are very large, and that is squared, right. Whereas here the liquid velocities are not going to be so large, so you need to make it up with a higher density liquid, which is why this strontium perchlorate is used. People have also thought about using a fraction of the exhaust gases themselves, taking a certain bleed from the combustion chamber and using it, but the trouble with that is you have to have leak proof valves that operate not only at high temperature but also at high pressure, which is not very easy. Okay. Otherwise, if there is a leak, there will be always a side force. So you do not want that, and therefore this kind of taking a certain bleed from the combustion chamber has not been pursued. So therefore you have to have a large tank containing this strontium perchlorate, primarily because if it needs to be injected at some velocity, the pressure here of the jet must be greater than the pressure here. So this tank needs to be pressurized, okay, and then the liquid has to be expelled under pressure. So that makes it a little more bulkier. But as I said, if you want to use gas injection, then hot gas handling is not very easy. Okay. In liquid engines, in some of the liquid engines, you usually have something known as a gas generator, which is used to run the turbine, which in turn runs the pumps. Okay. This gas generator also has an exhaust, which can be used in auxiliary nozzles to provide the kind of thrust vectoring that we want. So you will have small motors for that. If this is the main engine, you could have small engines that can be moved Okay, you could have these small thrust chambers which you can control and move the entire thrust chamber. That will give you the required side force that is required. Okay, but in this case the thrust vectoring that is possible is very small, not very large. Okay, so the only other thing that people have kind of thought of using but not yet looked at is in this case, instead of using a liquid, let us say one has a liquid rocket motor, a small liquid rocket motor, and inject the exhaust gases here. That could also give you the required side force, primarily because you will have a very high jet velocity. Okay, and if you want to switch off and switch on this, it is not very difficult because you are only going to operate the liquids, right. Switching on and switching off a liquid rocket motor is not a problem, but this is something that has not been pursued and probably could be pursued sometime later. There is also another method wherein if you have 4 rocket motors, okay, and the exhaust coming out through canted nozzles, right, something like this. Let us say you had 4 rocket motors, liquid rocket motors that are providing you the thrust, then you could have a situation wherein if you look at it from the bottom, let us say these are the exhaust ports of these 4 motors, you could increase the thrust and decrease the thrust in 2 of them to get your required control force. that is, let us say if you want to pitch up and pitch down, right. So you could actually increase the thrust of this to pitch up and reduce the thrust in this, so that this will cause a this will make the pitch, which if you are looking into the board, this will cause pitch down. Okay. If you are looking into the board, this will cause the vehicle to pitch down. Okay. And similarly you can have, this is for pitch, for yaw, increase the thrust in these two or the other two to get the required yaw motion. And you could also have roll using two of them in this fashion. Okay. If you increase the thrust in these two, then you can have, this is only possible if you have a liquid rocket motor and if you have 4 of them. Okay. If you have this is canted nozzle, so the thrust vectors will not be parallel, I mean perpendicular to the board, it is at an angle. So you will have that roll. Till now we have looked at this rocket propulsion course in this fashion, that is, we have not looked at what is the thing that is there in the thrust chamber. We have looked at nozzle, we have tried to derive equations to get the specific impulse of the nozzle. We have not bothered ourselves about what is the kind of engine that is there, liquid, solid or hybrid. Now let us look at in the next class we will start looking at the different kinds of engines, that is solid, liquid and hybrid motors. Okay. Thank you.